We're going to finish that forces inventory. We've got some friction stuff to do. I want to talk over some homework that you did for today. And then Monday, a reminder that at this point, we're still planning on doing that test. I think we're going to be in good shape, you guys. And remember also that you also need to turn in what on Monday then?
All your homework.
All the homework. So you give me a little packet of homework. I'm going to check it to make sure it's all done. Yeah.
Is this going to be on the test?
This content, is that what you're asking?
Yeah.
Yes.
Standard magnitude and stuff.
So, okay. So let me answer that question for everybody. So the question was, is this, and by this we're talking about the force inventory, is this going to be on the test? So, unlike some other classes, I don't think that physics is a recite kind of class. Physics is a use it and understand it and show me that you get it kind of class. So will you have to fill in a chart like this? Absolutely not. Okay? Which for some of you, the people that really like to memorize things, that's kind of frustrating, right? Because this is going to be like a can you use it kind of deal. So will you need to know this stuff? For sure. Okay? But it's not going to be like this. So it will be more like the problems that we worked on before and we're going to work on in a little bit. Okay? So like here's a situation and here's a box and it's, being pushed and there's some friction. Draw a free body diagram. Tell me what the force of friction is. Tell me what the normal force is. That's what we're going to be doing. Okay? So yes, it will be on the test, but not in this form. I just like to be able to organize things because it helps me then to solve problems and understand what I'm doing. Okay? So that's where I'm at. So friction, we did not fill in this box and we're going to fill this in a minute, but I want to finish up everything that we're going to do on this chart first so that you can just kind of set it to the side as a reference as opposed to having to fill things in. So we did gravitational force, we did the normal force, we did the frictional force. There were two other forces that we've talked about a little bit that I want to put in there. With applied force, he's like, I got this, let's do it. So we're going to put in the applied force. And this one is kind of funny because it's kind of like the catch-all for anything else that we aren't really describing. So this is really, and we haven't really talked about the deep philosophical situation with forces. Okay, let me write this down first, that this is just like some sort of person or object that's pushing or pulling. Okay. We haven't really talked about this, so I'm just going to do like a little tiny version of this. So in actuality, my friends, physicists usually talk about forces in one of two categories. So you can write this on the back if you want. I'm going to write it down below because I do want you to know it. So I'm just going to put it down here. So there are kind of two categories of forces. There are what we call in big air quotes contact forces. And this one's really wild and crazy, non-contact forces. I know, right? And I'm going to give you a different word for that in just a second, but I want you to just think about it in this way. So contact forces are things where there is contact, right? So I push or pull on something, that's a contact force. Okay? Non-contact forces are things like gravity and some other pieces, and we'll talk about what those are in a second. They're also called, in the more preferred reference here would be that they're called field forces. Okay? So contact forces are things where we think we're pushing or pulling. We've got field forces, and there are four of them. The four fundamental forces in the universe. Okay? This is like super big picture. Physicists are searching right now for that one unified version, unified way to describe all of physics. Okay, the grand unification theory. It's one of those things that I'm guessing within the next 20 years, somebody's going to figure it out, and maybe they're sitting in this room, and whoever figures that out, for sure will get a Nobel Prize. So, there is that. Okay? Opportunity for you right there. So, the field forces. Number one, I just heard somebody say it was gravity. Okay? Electromagnetism. Hold on, let's do one at a time. Hold on a second. Rudy, was that you? Who was that over there? Somebody was talking. Okay. Aiden said the strong nuclear. Say it with me. Nuclear. Nuclear.
Nuclear.
Awesome.
Nuclear.
A lot of times people, well, not a lot of times and not a lot of people, but sometimes people will say this thing that just makes my heart break and my ears bleed, and that is nuclear. Nuclear is not a word. Got it?
Nuclear.
It isn't. And it's not like even like a, oh, that's just going to make Carveling mad. It's like it's not a word we're going to laugh at you because you sound embarrassing. Because you're not speaking any English. Okay? So nuclear is talking about the nucleus of an atom, right? So the nucleus, strong nuclear force is a force that acts in the nucleus of an atom. And then do you know number 4? The weak nuclear force, yeah. Okay, so here we go. We're going to do one at a time. We're not going to get into them really deep because this is not where I really wanted to go, but I feel like I need to take the opportunity. Gravity is a force between any two objects that have mass. Massive objects, gravitational force between them. It's the one that we understood first. By understood, I mean observed. Could predict, right? I take a rock and I drop it, it falls, okay? The earth goes around the sun. Yay, gravitation, we get it. Not really. Gravitation is the least understood of the 4 forces. At a fundamental level, physicists do not understand how gravity works. We wave our hands a lot. We say, oh, we get it. Oh, sure. We've made a lot of observations about it. That's what we understand, but we don't really get it. So I'm just letting you know that. More opportunities, more Nobel Prizes out there for you, okay? So that's number 1. Number 2, we get really, really well. We understand electromagnetism really well. Electromagnetism is really all things with charged particles, okay? So gravity is 2 massive particles. Electromagnetism is 2 charged particles. They interact, okay? That's what we do. We will talk about this at the end of this year. We'll talk a little bit about it. Strong nuclear force. The strong nuclear force is, and I think this is so funny because a lot of people are like, first of all, you probably haven't heard of it. And second of all, once I point out, you're like, oh, that's really weird. So what is in the nucleus of an atom?
Protons.
Protons and some neutrons. So let's think about protons for a second. So you've got hydrogen, and hydrogen is just, the nucleus of a hydrogen atom is just a proton. Just a positively charged particle, no big deal. Got an electron going around, life is good. You move over 1, and you've got helium. Helium has what? 2 protons and 2 neutrons usually. But I want to talk about the protons. You've got 2 protons, 2 positively charged particles. According to electromagnetism, do positive charges want to hang out together? No! It's weird because you've been trained to think that 2 positively charged particles shouldn't hang out together. But in helium and in everything larger, they do. And it's pretty good that they do because if they didn't, we would not exist. Are you with me there? The universe would just be a bunch of helium. Or not helium, hydrogen, excuse me. It would just be a bunch of hydrogen. That's not very exciting. The strong nuclear force interacts between all protons and neutrons. Okay? Protons and neutrons have something special about them. That's, again, big air quotes. There are reasons for this, but I don't want to go into it right now. But protons and neutrons have this special force that glues them together. The gluons hold them together. Okay? That's what the strong nuclear force is. It's the strongest of the 4. The weak nuclear force is a little less strong than the strong nuclear force, but it's a whole lot stronger than gravity. We think gravity is really strong, right? Because it pulls us down. It's not that strong. It's the weakest of all 4. It's weird. It's weird. Do you want to know how I know that it's not that strong? Because I can totally overcome it every day, right? I can pick this up. Gravity's pulling it down, but I can pick it up. I'm way stronger than gravity. You with me there? Does that make sense? What's that? No, it's not. It's got water in it. I mean, you can pick stuff up. You know what I'm saying? Does that make sense? I can overcome gravity with no problem. I can jump. I've overcome gravity. You with me there? Okay. Can I fly? I don't know. I'm not going there right now.
No.
All right. Ladies and gentlemen. The weak nuclear force is the force that is responsible for all radioactivity. Okay? So alpha, beta, and gamma radiation all comes from the weak nuclear force. We will maybe talk about that after the AP exam because it's really interesting and fun, but we're not going to, it's not part of the curriculum for this class. 1, 2, 3, 4, you got it? These are all field forces. What does field mean? It means that there's nothing pulling or pushing, right? So if I've got this frog and I let him go, where does he go? Down. There's no string pulling him down. The only reason he falls down is because there's a field, a gravitational field that exists, something that's pulling him down. Electromagnetism, same thing, right? There's nothing pulling those charged particles together. It's just a field, an electric field. Whereas these contact forces are really us like touching, pulling, or pushing something. Do you want to know the secret?
No.
Okay, then plug your ears. Here's the secret. All contact forces are really just electromagnetism. All contact forces are really just electromagnetic. Yeah, I knew you really actually wanted to do this, right? So when I pick something up, friends, really it's just the charged particles in my hands interacting with the charged particles in the frog that cause that to happen. You ready for one more thing? One more thing. You know this from chemistry probably. What is an atom made up of mostly? Empty space. So here's the really weird thing. When I've got a frog sitting on a table, and you tell me, because we drew a free body diagram of it a couple days ago, that the earth is pulling down, that's a field force, right? And you told me that the table is pushing up. Here's the thing. The frog and the table aren't really touching. Because there are, like if you think about the atomic structure, there are little electrons at the very bottom of the atoms on the frog that are repelling the electrons that are at the very top of the very top of the very top of the table. And that's really why the frog doesn't go anywhere. It's really electromagnetism. And it really is that you're not touching anything. So this is one of those times, and I know that this is going to come back to bite me in the later with my children, because I know that they're going to use this against me, okay? But the thing is, right, I know because I know many of you have siblings. You know that whole, she touched me, you know what I'm saying?
No, I didn't.
And so she's going to be like, I didn't really touch her, right? Because there's really no contact. You see what I'm saying? Yeah, so it's really true. Now, there are counter arguments to that. But really, are you touching anything? I know. It's going to happen. It's going to be sooner than I think. I'm going to be cheap. They're going to use physics against me.
There's only
There is no fusion happening in that. I'm sorry.
That means nothing is
Exactly. All right. All right, come back. So now that I've totally, hopefully messed with your head, that was kind of my goal, okay? This gravitational force is a field force. The normal force is really just an electromagnetic force. You don't have to know that. That's just an aside. Just, FYI, Ms. Carbling wanted to share that with you. Friction, again, really just an electromagnetic force, okay? Applied force, again, really just an electromagnetic force, but at the macro level, so that's really at the micro level. Are you with me there? So at the micro level, that's really true. But for what we're doing in this class, we are going to call those forces by these names. Because otherwise we're saying electromagnetism this way, electromagnetism this way, and then it gets really confusing. You with me there? Does that make sense? Okay, so big picture, we've got applied forces. Now let's write this down. Here we go. So the direction of the applied force, it's just going to be in whatever direction we tell it, right? There's not a secret to that. So that's just read the problem. I'm just going to put that in parentheses because that's really what it is. The magnitude, again, read the problem, right? It's going to vary. Is it able to cause an acceleration? Yes. For sure. It could slow things down. It can speed things up, right? I applied a force, an applied force. We did this yesterday with the ball, and I sped up that ball. Harrison was over there, and he slowed down the ball, right? So it can cause positive or negative accelerations. It can also cause circular accelerations. We'll get there, not today, okay? The diagram, literally, it's just going to be in whatever direction it's in. Oh, touching the box, though, right? The force of the person on the box or on the object. This one is kind of the catch-all. I think I said that just a minute ago. But the applied force is just kind of all the catch-all. All right, we've got gravity, normal force, friction, applied force. There's one more. Everybody's favorite. What was it? Tension, yeah. Here we go. That's FT. The object pushing or pulling for tension is usually a rope, right? A rope or a string. Okay. The direction is just along the direction of the string. Okay. Magnitude is, so this would be like a read the problem or use the FNet equation, depending on what it says. Okay, so I'm going to say use FNet or see the givens. Okay. Is a tension force able to cause acceleration? Yeah. And so then you could draw yourself a picture like with some ropes hanging down like this. Maybe you've got a box that's hanging on some ropes, and the force of tension is going to be here, F of the rope on the box. Maybe there's another F of the rope on the box. How are we doing, team? Okay. I don't have any others to go on here right now. But I think I mentioned to you yesterday that I give you that bright colored piece of paper so you'll hold on to it so that it stays in your notebook and you can find it later. So, what's that? But don't lose it? You know, I didn't think of it, friend. And I will, the next time I do these, I will. But I'm not going to make you a new one since you already wrote all up.
Can you give me your native access?
If you go down to the library, you can ask Miss Kay, and if she asks, then tell her it's for me. I'm okay with that. All right, except, hold on, Harrison, you don't want to do that because we're going to write more on it. So don't do that. And then it will rub off, and then it won't help you anymore. All right, ladies and gentlemen, I would like, let's see here. I want to just peek at this question. Yeah, I want to do this question real quick. A quick ranking task for you. I've got packages with different masses moving on a constant speed conveyor belt. So think maybe like airport with your luggage coming back, or I don't know, like other conveyor belts you've seen. That's just the one that pops in my brain. At the instant shown, all the packages have the same constant velocity of 2 meters per second directed to the right. The packages do not slip on the belt. All the masses given in the diagram are in terms of m, this mass of the smallest package. Rank the magnitude of the net force on each package. I want you to think about this yourself first. So no talking right now. I just said no talking, right? We're listening. Yeah. I'm going to give everybody a chance to take a look, to think this through. All right, have a conversation at your table, go.
Yeah, so the acceleration. Yeah.
Oh yeah.
But if they work, so
Temperature's very misleading.
yeah, you're right.
No, what is you evolve?
How are we doing? We have an answer?
It's all zero.
Yeah?
You have a 2 molar solution in box and a 4 molar solution in box. Which one is more concentrated?
That's not the question. I mean, there might be ranking tests for chemistry. There probably are somewhere. I don't have them up. Because I do physics. All right. What's the answer? What's the answer? What'd you say, Nick? I thought that was your voice before. Who said that a minute ago? Was it from over there? Was it you that said that? Okay. Yeah. They're all the same. They're all the same. It's a lie? You don't believe it? What do you think?
I said D is greater than B, which is greater than C, which is greater than A, which is greater than B.
So, how did you make that decision?
Because gravity, I just multiply gravity close to each one.
Okay. So you figured out, so you got, this one has the biggest mass, so it's going to have the biggest force? Okay. Okay. That is not what Nick said. Gunnar, what were you going to say?
They're all zero because they're at constant speed.
Okay. So tell me more about what you're saying.
Well, because they have a constant velocity, the net force would be zero because all the forces would be canceled out.
So if we're going to draw the free body diagram for block D or box D, what's the free body diagram going to look like? It's going to be, there's going to be the force of the earth, right? On the box. There's going to be a force of the, what is it called? Conveyor belt on the box. Any other forces acting? Conveyor belt's got to be pushing. And there's what else I heard somebody say? Friction. There's an applied force going this way. Yeah, there is. Yeah, doesn't it say? They do not slip. Yes, there's got to be some friction. It's got to push it. It's got to push it. Maybe not? You don't think so? Once it's moving, it's moving?
But like the box isn't falling off.
If it doesn't,
The box isn't making, I mean, the belt is making it move.
Yeah, yeah. So it depends on, I mean, there are certain cases here, right? And so, shh. Listen. Once it's moving, does there need to be friction acting? I don't know. Go.
Is this the same thing as like when you're in the car and then like it's moving really fast, but when you're in the car you're not necessarily looking to it? No.
Yeah. Did you guys hear what he just said?
No.
Say that really loud because I want to make sure everybody.
Sure.
It was a great example. That's why if it was wrong, then I would have just said, I'll move on. But say it again.
If you're on a highway and the car is moving fast, nothing's moving inside the car.
Because you are moving at the same speed that the car is moving. Right? Is that what you kind of mean?
hey, what if you throw?
What happens to your pen?
It moves fast.
It goes straight up and down. Try it this weekend. Maybe not with a pen, but take like a little paper ball or like take your frog, right? And throw it up in the air. Okay? Now, here's the thing. This is kind of an interesting question. And I'm really glad that it came up. Let's think about this really carefully. If you're in a car, or another way to think about this is like on a moving sidewalk. Do you know what I'm saying? Like if you're standing on the moving sidewalk, okay? So when you first are getting on the moving sidewalk, or if you can imagine, I've never had this experience, but let's just imagine if the moving sidewalk wasn't moving and then all of a sudden it started moving. If it had no friction, what are you going to do?
Slip.
You're going to fall, right? Probably or slip or something, okay? But if there's friction, then you can go along because the conveyor belt is pushing you this way, and friction is opposing the motion, so you can stay there. Now, once you're moving. Let's think about this. if you were moving along something and there was no friction, could you stay there?
No.
Stay in one spot.
Yeah, could you? Yeah. Could you stay in one spot relative to the moving sidewalk? I mean, say again. Then you would. Yeah. We will get here later. I like this. I like that little conversation. I don't think you actually need the friction once it's moving, but to get it to move, there has to be no slipping, so there has to be friction acting. So since it's moving, it doesn't have to. But regardless of that, regardless of the friction, no friction thing, the key is that the speed is what in this case? Constant, which means that we're talking about it right now, right? And we remember from our conversation earlier, where did it go? Oops, come back. That for non-accelerating motion, the velocity is constant and the net force must add to 0. How are we doing? We okay? Sweet. All right, we got to keep cruising. So the answer for that one was they're all 0. Boom. All right. Let's talk about friction. Let's talk about friction. Here's the situation. I really like this question. I'm going to use this box, and so this is going to be my mystery box for right now. Okay? I can hold this box up against the wall. You watching? Everybody see it? Can you guys all see? Okay. I want to know, actually, really what I want you to do is I want you to draw me a free body diagram. Free body diagram of me right now. Here I go. Draw a picture. Right now. Here I am. You guys all watched me just kind of put my hand down. You okay, or do you need me to stand here as a model? All right. I'm moving. My arms are sore from this morning. Talk to your table mates if you haven't started that conversation already. What forces are acting? Figure it out. You have a whiteboard on your table except my back friends, but I'll get you one in just a second. Draw a picture for me.
Yeah, it would be up relative to the wall. Because gravity is pushing down.
All right, are you ready to show me pictures? Draw them on the whiteboard, please, so I can see them. Draw it big, label it correctly. Make sure it's labeled just as you will on the test on Monday. Get that practice in right now.
The other on this side,
Just deal with that.
just the gravity. Okay, so
We
the normal force is equal to the y force, right? Like this, and then friction is opposing gravity. Stop. Also, why did we draw it from the other side of the room? We're on this side. The wall's on the left. Her perspective would have been like this.
That's actually the best.
Make it 3. Oh yeah, we erased the thing. Just 3 million. Erase the whole diagram. So minus points right there.
Well, I mean, we will talk about what it means to have I think you're just parsing.
That would be
Scratch me. Rudy like with yeah, you just run away.
Why don't we test this thing? Everybody get my car.
it's like with the babies act.
No, but I would still
It goes like on your shoulder, right? Yeah.
Okay, so like
Cardiac times 3.
All right, ladies and gentlemen, let me have your attention back here, please. I love the conversation that's happening. I love the struggle. It's important to have to grapple with this stuff. If the stuff was easy, we wouldn't do it. You would be moving on to a different class. I want you to be challenged at least, once in a while. So, or maybe every day, maybe all the time. We've got some forces. Tell me what one of the forces is. I need somebody to tell me a force. Get me started. Go, Harrison.
the normal force.
The normal force. Which way does the normal force go in this case? There's a way you could describe it without having to do the dance. Away from the wall, because it's always what? Perpendicular to the surface, right? Normal force, always perpendicular to the surface. So it's got to go this way. This is the force of the wall or the board or the whatever you wanted to call it on the box. And what kind of a force is that? You just told me? Normal force. What else you got? What else you got? Go, Nick. I'm sorry, I couldn't hear you. Say it again. Force of the earth. Which way does that one go? Down, because it always does, right? Always down towards the center of the earth. It's still down. Now, I just want to remind you that you need to get in this habit because guess what? On Monday, I will have you draw at least one free body diagram. And guess what? If you just write FG here and FN here, it will be wrong. Okay? So just friendly reminder that it's got to be object on box, every single time. Every single time. All right. That's 2. If there were just those 2 forces, the box is going to go, that would be accelerating motion. We're not doing that yet. That's next week. Go. The force of me on the box. Which way did I push? That way. Toward the wall. Toward the wall. The force of Miss K on the box. What kind of a force is that? Awesome. At this point, where's the box going to go? Down. Did the box go down?
No.
So there's got to be something counteracting it. What is it?
Friction.
Friction, right? It's friction. For sure. Why is this problem weird?
Because it's not actually.
Well, it absolutely isn't moving. You're right. But the thing that causes, like, the reason I do this problem all the time is because we usually think of friction as, like, moving this way. But in this case, friction is going up. If the friction were not there, it would go down. You with me there? Yeah. So the friction is what's causing this to not accelerate. I don't know if you've ever ridden in one of those rides. They used to have one a long time ago. By a long time ago, I mean, I don't know, 5 years ago at Adventureland. They have other amusement parks. The ones that spin you around and you stuck to the wall. The silly silo were similar. Okay?
Yeah.
We'll talk about it more in just a minute, or not just a minute, but, in a few weeks, how that really works. But the reason that when the floor drops out, you don't fall down is because the force of friction pushes you up. We'll talk about why that happens another time, but that's just a heads up. Now, we need to talk a little bit about how friction works. Okay? So there are two kinds of friction. One that we're going to spend lots of time with, and another one that we'll kind of deal with a little bit. And I will tell you guys, we're not going to get really, really into this today and before this next test, but I want you to be aware of it, and then we'll get deeper in there later. So here we go. Friction. Let's talk about it. Friction always opposes motion. So I want you to imagine that you have the opportunity to help somebody move a really large box. So like I'm thinking, like a box that has I don't know, a refrigerator in it or a bunch of books in it or something that makes it really, really heavy, okay? And you, in order to move this thing, are going to push on it, okay? In order to do that, if you imagine that, hopefully you've had some sort of experience with this before, especially with something large, you've probably experienced the fact that when you push on it, it takes more force, more effort to get it started moving. Are you with me there? And once you've got it moving, then it's easier to push. The reason for that is that there are two different kinds of friction. The first one is called static friction. The word static just means, anybody know? Staying still or not moving. Yeah. So static friction just means that it's not moving. The other kind of friction, there's a word that starts with a K that means motion. Does anybody know what it is? Kinetic. Oh, look at that. You guys are so good. All right. So static friction and kinetic friction, they're both calculated in a very similar way, but they're different, and I want you to know that that's true. So the funny thing about the frictional force FF is that it is absolutely dependent on normal force. That's kind of weird. But it kind of makes sense. Let me tell you why I think that. If I apply just a really slight force, what happens to my box? It falls. If I apply a bigger force, well, not so big, but a bigger force than I did before, if I apply a bigger force, that means I apply a force this way, so the wall is going to apply a force that way. That's the normal force. Are you with me there? The normal force is responding, not really, I hate that, but I'm just going to say it kind of like that. The normal force is going to be as big as my applied force. You with me there? Okay, kind of like when we were carrying those plates. So the normal force is going to get bigger as I apply a bigger force here until I break the board. As the normal force goes up, the frictional force goes up. The harder I push, the more friction there is. That's nice. So that's how it's related. So let's kind of put that together. So FF is related to FN, and it's also related to the two materials. So if I had a carpeted wall, it would be more friction, right? Because it's a rougher surface. Okay? If I had something really smooth, I don't know, like a whiteboard and a Kleenex box that are both pretty smooth, then the amount of friction that I have is much smaller. Are you with me there? Does that make sense? And the way that I quantify that proportionality constant that goes right in here, it is called the coefficient, C-I-E-N-T, of friction. And it is a quantity that you can determine experimentally based on two materials. It's basically how slippery or sticky two materials are when they're rubbed together. That's what it is, okay? So it's how hard it is to get them to move apart or how well they just slide. The coefficient of friction is marked with a funny little letter. It's a Greek letter. It's up there. Boom. Looks like a capital M. The one right next to it is the little one. It's not M though, it's mu. Mu is what it's called. Mu. Okay? The Greek letter, it looks like mu, mu. Okay? There is a coefficient of static friction, mu s, and there is a coefficient of kinetic friction, mu sub k. All right? Mu sub s is the static friction coefficient. Mu sub k is the kinetic friction coefficient. And because it is easier to push something once it's moving, we know that the coefficient of kinetic friction is always going to be less than the coefficient of static friction. It's always going to be harder to get something to move than it is once it's moving. We doing okay? Does that make sense? Okay. So we can write it like this. We can say that FF, kinetic, and sometimes they just write it FF. Sometimes I write it FK. I'm not going to be really concerned about how you do it because we're not going to calculate it all that often. I want you to understand the concept more than getting like worked up about how I write it. Does that make sense? But the force of kinetic friction is equal to mu sub k times Fn. So they would give you mu and they would give you Fn, or you could find Fn and then you can find Ff. We okay so far? Static is a little bit different. The force of static friction is less than or equal to, what? Let me write it down, then we'll talk about why. Mu sub s times Fn. Less than or equal to, that's not how we normally write a formula, right? That's strange. But we can understand it if we think about a box on a surface. If I ask you to draw a free body diagram of this box, just like this, is there any friction acting? No. Why would there be? You've got the earth pulling down, you've got the table pushing up, life is good. If I start applying a force, if I apply just a little tiny force, there's a little tiny frictional force. You with me there? If I apply a little bit bigger force, there's a little bit bigger frictional force. These are all static force. You with me? Okay? Once I apply a big force, it's going to start moving, and then I'm just always going to have a constant force pushing back. How are we doing? We okay? Okay. I want you to look at one question before we go, which is what I wanted to get to today. So here it is. It's kind of a thinker, but I think you can do it. It's that crazy mystery box one more time. 10-kilogram mystery box rests on a horizontal floor. Okay, we've got some numbers here, friends. The coefficient of static friction is 0.4. The coefficient of kinetic friction is 0.3. Remember I said that the kinetic friction is always going to be less than the static. Determine the force of friction acting if a horizontal external force is applied. So let's draw ourselves a picture. Just real quick here. Here's my box. Pick a force, any force. What force do you want first? Gravity, the force of the earth on the box. Anybody else? More forces? Normal force, which way does that go? Always what to the surface? Yep. What else you got? The question is about friction. So that's going to be the force of the surface on the box this way. And then we got an applied force. Oops, force of the person on the box, FA. What's what? My handwriting's kind of icky there. I apologize. From this person who's pushing on it. Applied force FA is exerted on the magnet. Yeah. Okay. I want you to give it a shot. I want you to talk to your table, and I want you to see if you can figure out how to do this question. There are 5 parts, but it's not so hard that you, like, once you figure out what to do, you're going to be okay. I want you to chew on it for a minute, and then I'll talk with you. Sound good? Question, though.
So you just, since it's not stated, you just said that since the applied, you just guessed, like, applied force going this way, and then you just have the opposite.
Yeah. All I know is that the applied force is horizontal.
Yeah.
So I picked a direction.
So, okay.
And I know that friction is always going to oppose the motion. Does that make sense?
Yeah.
Good question. Thank you for asking that. Okay. Go. Have a conversation. See if you can figure it out. Talk it out right now. Go, go, go.
What do we figure?
Yeah.
Well,
Did it say
okay, so it's like A is 0, so to calculate the friction and static, you just plug it into this.
It's turtle on an alligator.
So it's just
Is this a bib?
What? No, it's just like a little washcloth when my kids were little.
Oh, it says cute.
Yeah. I didn't pick it out just for you. Or maybe it was fortuitous. I don't know.
Capitalized is the 3rd letter, but not the 4th.
I don't know what it is. I don't know what to do.
He doesn't understand. It's just really.
So for
Can I touch base with you for just a second? You don't have to be done, but I just want to like maybe try A with you. Is that okay?
Yeah.
For A, if there's no applied force, you're totally laughing. You're like, compound. If there's no applied force, how big is the friction going to be? Okay, that was easy. All right, I'll do one more with you. So A, the frictional force, friction, is going to be 0. How about for B? Let's write down an F-net equation in the x direction. What forces are acting in the x direction? Friction? Perhaps. And what else? The applied force? Right? What about in the y direction? What's acting in the y direction? The normal force and gravity? And what does the F net in the y direction for sure equal to? 0, because it's not going up or down, right? So that means that from that, we can do this in our head pretty fast. This is going to be 98.1 in the downward direction. So it's going to be 98.1 in the upward direction. Everybody good there? Okay. So it's going to be 98.1 equals Fn. That's helpful because we'll need that for FF. We know that mu sub k is 3, or excuse me, mu sub s is 4.0. We know that the force of static friction is less than or equal to Fn. Can somebody plug this in if you haven't done so already? 0.4 times 98.1. What do you get? I don't remember what the answer is. 0.4 times 98.1. Who's got a calculator? Do it quick, quick, quick. What is it? 39.24? In situation B, the applied force is 10. What's the frictional force going to be? If I push with 10 newtons one way, is the frictional force going to be 39.24? No, because that means that it would go backwards. Is the box going to move? No. So what's the frictional force going to be? 10. How about for C? Same situation, right? Now I'm pushing with 20 newtons of force. If I push with 20 newtons of force, can I overcome my static friction force? No, because my static friction is just going to go up, 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 up until it gets to this, right? So if I push with 20, what's friction going to push back with? 20. All right, how about for D? If I push with, convenient that they said 38, right? If I push with 38 newtons of force, what's friction going to push back with?
38.
38 newtons of force. Are you guys with me there? Is that making sense?
Yeah.
Once I push with 40 newtons of force, now what have I done? I've overcome my static friction. So now, oof, I got that box to move. Is the frictional force going to be 39? No. What's it going to be? What? Say it again. What's that?
0.3 times 98.1.
0.3 times 98.1, whatever that is. Somebody tell me. Ah! Something. 29.43, and that'll be FF. Okay, ladies and gentlemen, we are going to test on Monday.